Hello. In this video we will learn how to design a P-only controller, a member of the PID family, using the root locus. This is the simplest type of PID controller that you can use. And the root locus is one way to design these controllers. The second way being frequency response, or Bode plots, which will be covered in a separate video. What you do with a P-only controller, you have, of course, in a PID controller, three different controller gains: the proportional gain, the integral gain, and the derivative gain shown here. The integral gain and the derivative gain are both zero, so we have what's called a P-only controller. This is the simplest type of controller, and as we'll see, it does not change the root locus of the existing open loop transfer function. GOL stands for open loop transfer function. What happens with a P-only controller is that you change the gain of the controller, and it actually moves the closed loop poles along the existing root locus to a point that is a desirable point from a performance standpoint. We will use two examples to show how this is done, a first order system and a second order system. So just as an example here, I have a first order system that has a time constant of 2 seconds. And there are many systems like this. A tank has this type of transfer function, and many other things. A motor has this type of transfer function also, an electric motor. So what we have here is we have a system that takes 2 seconds to reach 63.2% of its final value. We want to double the speed of this controller, so we're going to close a loop around the system, be it a tank, a motor, or whatever, and then we're going to adjust the controller to speed the system up by a factor of 2. We have a pole at minus 1 over the time constant. Poles, I don't want to go into this right now, but poles are actually values of S that will make the denominator of this transfer function equal to 0. So if we put in minus 1/2 here for S, that will turn this into minus 1, and then the denominator of the open loop transfer function will be 0. So this is the system that we start with before we put the controller on it in open loop. And what we want to do is move the pole out so that we have a time constant of 1 second. The time constant is always, you get the pole location. Well, the pole location is minus 1 over the time constant. So what we can see here by moving this out to this point, this is at minus 1/2, this is at minus 1. The time constant of the closed loop pole, if we move it out to this point, will be 1 second, and so the closed loop system will be twice as fast as the open loop system. Again, these yellow crosses are the open loop poles, and the pink rectangular symbols are the closed loop poles. So we're going to move our closed loop pole out to this location, which will give us a time constant of 1 for the closed loop system. We're going to use a graphical method to solve this. So what we do is we only have one open loop pole and one closed loop pole. So we draw a vector from the open loop pole to the desired location of the closed loop pole. And as you can see, this vector has a length of 0.05, and we'll talk about its angle in a minute. You always measure the angle of this vector from the positive real axis. So there's only one such vector, and that angle is 180 degrees. The way that you design controllers using the root locus is you have to meet what's called the angle criterion and the magnitude criterion. That's covered in a separate video also on the root locus and using the root locus to design controllers. So we've met the angle criterion because we only have one vector, one closed loop pole, I think I have this in the next slide. Yes, here's our angle and magnitude criterion right here. What has to happen is we have to have the gain times the open loop transfer function is equal to, has a magnitude of 1 and an angle of plus or minus 180 degrees. This graphical method of solving shows that a way to evaluate a function like this, a function that has zeros in the denominator and poles in the zeros in the numerator and poles in the denominator, is to use this graphical method. And then the angle is the sum of the pole angles minus the sum of the zero angles. So if we apply this graphical method to our example here, our example is fairly simple. We have to have Kp here because I think it says in this problem statement that the gain of the open loop system without Kp is 1. So the gain of the open loop system with Kp will be Kp. And then this 1 over 0.05, the 1, there are no zeros, so the product of the magnitudes of the zeros becomes 1 in that condition. And then the product of the magnitude of the poles is 0.05 because there's only one pole vector and its length is 0.05. So this is the when you don't have any zeros, you replace that with a 1 when you have a product mathematically. When you do have, well, this would be the product of your magnitudes of your pole vectors, and we only have 1, so it's a product with a multiplicand in it, and that is this 0.5 here. And then the angles that we have here, if we look at our formula, the angle is the angle of the pole minus the angle of the zeros. And I'm not sure why I have this 0 right here. I think that's a mistake. So this should not be here, and this should just be the sum of the angle of the poles is negative 180 or 180. It doesn't matter which one you use. If you measure this way, you get 180. If you measure this way, you get negative 180. And then the angle of the zeros is there's no zero vectors, so a sum turns into a 0 when it doesn't have any components. So our magnitude criterion is met. To meet the magnitude criterion, this whole thing here, which is the magnitude of this vector Kp times the open loop transfer function, has to be 1. We have this 0.5 in the denominator that comes from the magnitude of the pole vector, so we actually have to put a 0.5 in for our gain. So this tells us what the gain of our controller needs to be in order to move the closed loop pole to this desired location. This is a second order system, a little more complicated, obviously. There's two open loop poles, two open loop real poles. I say here that the open loop gain without Kp is equal to 1. So we need to design a controller to minimize the time to peak value, but we don't want to exceed 10% overshoot. So these are our performance criteria that we need to meet, and we need to design this controller. So the first thing to do is to draw the root locus, and when we have two real open loop poles like that, the root locus just is in the middle here between those two. These two, when you turn the gain up, this pole moves this way, this pole moves this way, they meet in the middle at negative 4.5, and then they depart and go into the imaginary part of the S-plane. So, let's see what we need to do. We have a criterion that we cannot exceed 10% overshoot. Now, the other criterion is we want to maximize the peak time. The peak time, as you can see in a video that I haven't put up yet, but the peak time is measured by the distance out away from the real axis. So we want to be as far away from the real axis as we can, but we do not want to exceed this 10% overshoot. Now, the 10% overshoot, there's a relationship between zeta and overshoot. It's just a direct relationship between the two. It's a little bit complicated, but this shows that relationship. We need to have a zeta of 0.591. If we have a zeta less than 5.1, then we'll have greater than 10% overshoot. So that limits where we can go. And the other thing in this geometry of second-order systems, what this means, there's a relationship between this angle theta, which you'll see in just a second, and this and zeta. Basically, theta is equal to the arc cosine of zeta. And that means that that angle, which is shown right here, you draw a ray from the origin, and you go up from the negative real axis by that amount, and the arc cosine, or the cosine of this angle, is equal to zeta. So what this means now is we want to put, like I said, for minimum peak time, we want to be as far away from the real axis as possible, but we can't go to a zeta lower than 0.591. Now, the way the tangent or the cosine works is if we go further up, the cosine of 0 is 1, the cosine of 90 is 0. So this direction here is actually the direction of decreasing zeta. And we will wind up with a higher overshoot if we go into this territory here. Down here, we're okay. The overshoot will be less than 10%. But if we put it right at 10%, that will put us at the maximum distance from the real axis that we can be without having too much overshoot. So let me see what I have next here. We'll put the closed loop pole right here with this angle here. And then it has to be on the root locus because this is a P-only controller, and with a P-only controller, you just move the closed loop poles along the root locus. Okay, so we'll use the graphical solution again. This is where we want our closed loop pole to be. We draw our magnitude vectors. We have no zeros, like in the last example. But we do have 2 poles instead of 1, so we have to draw 2 pole vectors that go from the open loop poles to the closed loop pole. And these I have labeled MP1 for the magnitude of the pole 1 vector, and MP2 for the magnitude of the pole 2 vector. You measure the angles of these vectors from the positive real axis, so from here over, and then from here up. So let's continue with this. And as it turns out, because of the rules for drawing the root locus, this ray that goes out, or path that goes out from the real axis, has to be halfway between -6 and -3. And what that means is that actually this angle, this is an isosceles triangle right here. And this angle here has to be equal to this angle here. Okay? So both of these angles then are the same, and this angle here is theta P2. It's the same as this angle right here. So if we look at our magnitude criterion, remember it's the sum of the pole angles that count, and because of the geometry, the sum of this theta P1 and theta P2 is 180. And that means this is actually a statement that this line here, a vertical line through the center of the midpoint between these 2 poles, will always have that property, and that means that this is a path of the root locus. Okay, so we have the angle criterion satisfied, which is the first one we want to satisfy, and now we have to satisfy the magnitude criterion. which is, I just said all this. So the magnitude of the open loop transfer function can be graphically calculated using this formula here, Kp times the product of the z magnitude vectors divided by the product of the pole magnitude vectors. That has to be equal to 1 to satisfy the characteristic equation of, the characteristic equation of this system. So we wind up with this formula for this particular case. We have no zeros, and when you have a product and you have nothing that you're multiplying together, that turns into 1. But we do have the two pole magnitude vectors, which actually happen to be equal in length. I think I say this here. And this is a calculation of what this point is. Obviously, since this point is halfway between -3 and -6, it's at -4.5, and there's the real part right there. And then the imaginary part, well, we know this real part, we know the adjacent side, and we know the angle here. So we can simply use our tangent formula, multiply the adjacent side times the tangent of that angle, and that will give us this the length, the distance from the real axis up to the closed loop pole, which is the same as the imaginary component of that coordinate, and that turns out to be 6.15. There's actually another pole down here, but like we always do with root locus, we only look at the top half because the bottom half is exactly like the top half, so there's no reason to analyze the bottom half. So this is where our closed loop pole needs to be, and then that gives us actually the angles, or the length, the magnitude, sorry, of both of these vectors are the same. So let's continue on with that, and that's what's going to happen here. So here is just using the Pythagorean theorem with this geometry. We find out that the magnitude of the these two magnitude vectors for the poles is 6.33. Okay, and to meet the magnitude criterion, we have to have, if you look at this equation right here, if we multiply both sides by MP1 times MP2, we have an expression, a closed loop expression for Kp, and we find out that Kp needs to be 40.1. So we put a P-only controller in on this system, close the loop, and then we have a system that has less than 10% overshoot and is at the it reaches its peak time as fast as possible. And that's the end of this. There are more videos coming. I'm starting back up again to make videos. I have a lot to make, and I'm going to commit some time to doing that. So thanks for watching.